All right, and now let's look at limits at infinity. So we're going to be looking at those limits problem where we're finding limits when we're letting x getting close to infinity. So limits at infinity. And so allow me to briefly remind anyone viewing this video about what we have been doing so far. But so we started out studying calculus, and it's the way it is. Anytime anyone starting to learn calculus, we have to start out with learning limits. And so just the same way here, I believe before you came to this video, then you must have watched my earlier video lectures about a lot of the limit techniques here, or techniques to find limits. And then at a certain point, when any of you feel comfortable enough with finding quite a few numbers of limit problems, then I kind of took things in an off direction a little bit. So in my most recent lectures right here, I've been doing and discussing about continuities and all that, but in the end, it's all limits that apply on top of that. And then at this point, we're going to come back to look further into different kinds of limits problems right here. And so here, allow me to introduce limits at infinity. And so it's just the way how it is. As now your majority in math and is particularly learning about limits has grown and has grown further. And here you are ready to learn about limits at infinity. And so by far, briefly remind yourself that on any function you have been able to find limits when x is being allowed it to approach a particular limit point. So these, x coming close to a has been like a is a 5, a is a 3, a is a negative 10, a is a 0, a is whatever. But these limit points right here, these were finite limit points. So that a right there in particular was representing a finite, and our terminology back then, limit point. And finite means knowing exactly where any of these limit point is on the x-axis. So sort of like we know our destination. But now, that's not what we're learning, because I believe anyone at this point of viewing this video is well familiar with that. So we're not looking at limits when x is getting close to a finite limit point anymore. We're done with that. Now, the whole idea of limits at infinity now is that with a function given, with a function f of x given, we still want to find limits, but we want to find the kind of limits where we're letting x getting closer and closer to positive infinity. So wait a minute. Infinity is not even a number. It's not even a finite destination. So the proper way of saying now is that we're going to find a limit as we're letting x keep growing larger and larger, or growing positively to positive infinity. And that's the true understanding. And this is what it means by we're taking limits at infinity. Same way, if we can let x to grow to positive infinity, then on the same function, we can also consider the limits of this function as x being allowed it to head out to approach negative infinity. And once again, remind yourself, negative infinity is not a finite point. It's not a finite limit point. It's not a finite destination to know. It's only a direction. So we're letting our function approach as x is keep going further to the left, further to the left. So graphically speaking, we have a function, and any function has a graph. So f of x has a graph. It could be something like this. All right, so limits of f of x as x getting close to positive infinity means we want to find out what happens to the function value as we keep letting x grows bigger, and grows bigger positively. And same way, if we, on the other hand, if we want to find out and study what's happening to the function outputs when we're letting x getting further to negative infinity, then here we formulate our problem as limit of f of x when x is getting to negative infinity. We're letting our x value becoming more negative, and further negative, and further negative. All right, and so after some introduction like that, let's get to a couple of demonstrating problems. So I'm now going to erase what I wrote here. Okay, so we started out learning how to approximate limits earlier in the quarter by doing constructing table of values. The same exact idea works out here, because the table of values, and it's me as well. I personally believe that it's the original idea of finding limits. And then once we're getting so tired of going with table approach, then we're going to start hunting for a more effective solution to find the any limits problem. So same way right here. So now since we're being thrown into a completely brand new kind of limits problem, we have to go back to the ground, use a table approach. So it's sort of like that's a zero ground for us. So let me bring up an introduction problem right here. About let's evaluate, and our function here is the x squared function. Okay, and we want to find out what's the limit of this function if we let x come close to or getting further to getting to positive infinity. So we're letting x approaching positive infinity, and so we can, and it seems like a lot to construct a table of values, but at this point, once everybody has already comfortable with quite a few lectures, including doing your homework assignments, then you should be moving on pretty quickly with this problem right here. So as far as table, on the same function here, then how do we describe the idea of letting x approach positive infinity? We can start out with 1. The output value is 1. Simply just that. Then we can quickly grow to 10. See, getting bigger to the positive side. So x equals 10. The output value is 100. We can quickly jump to 100 for x. And our value here is now, oh boy, it's getting real big right now. Okay, 10,000, because it's x squared. And then we can quickly jump to 1,000 as the inputs. The idea here is we want to keep letting x become positively larger and positively larger. And so we're looking at what? 1 million. And so now, oh boy, I really don't want to, and I don't think we need to go any further, but now anyone viewing the video here together with me can start making an estimate right now that for x squared, particularly as our function right here, if we let x approach positive infinity, pause the video and make a quick estimate and then resume, and I'm going to show the answer together with you guys. All right, so everyone's back. So the answer is positive infinity as an estimate right here. And graphically speaking, let me now bring up the graph for our function here. And computer takes time a little bit, but all right, so there we go. So let me now quickly point out that x squared, and its decimals, that's quite useful for me for any of my instructional demonstration here. All right, so the graph of x squared is that famous parabolic shape there. All right, and let me zoom in further. And I'm not even going to bother showing the axes number as well as the grade 3. I'm going to hide all of those away. The idea now is that as we let x, and observe my mouse cursor right here, but as we let x getting further to the right hand side, that's how my mouse cursor is doing, is indicating the fact that we're letting x approach a positive infinity. And so as we navigating to positive infinity, then our height of the function keep growing and keep growing and keep growing unboundedly. I can even drag the graph or even zoom further out on the graph and keep dragging so that you can see further. And so the height of the graph, the vertical height, will keep growing up and growing up. And that's how it makes sense with our understanding that, give me 1 second to get back to my screen here, but so that's how graphically it also agrees with our conclusion earlier that this function x squared, as we let x getting close to getting, I shouldn't say close, as we let x approach a positive infinity, then the limits there, the function itself grows to positive infinity as well. And so that's the end of this particular little problem. So it turns out not as dragging as anyone before we saw this thought. But now let's look into another problem. So what about the same function right here, x squared? Let's not go anywhere outside of that, away from that function yet. X squared is our function. But now I want to consider the limit of x squared as we're letting x we're letting x approach negative infinity. Negative infinity. Okay, so let's quickly construct a table of value again. So for table of values, this time x squared, let's choose input -1. And so -1 being substituted into the function, our output for this function is +1, as anyone already knew it. How about we quickly jump to -10? We want to choose these x values that, and like you have already seen back in the table idea, that we have to choose in a way that anyone seeing your work is understanding that you're letting x values going to negative infinity. So -10, +100 is the value for the output. -100, your output here is going to be positive again. It's just the way how the square operation works. And of course we're squaring including the negative here. So 10,000. And then how about -1,000? See, we keep letting x grow negatively larger, negatively larger, and negatively larger. And so our outputs here, 1 million. And so now once again there's no need to move on any further to put in any more entry, but now anyone viewing this video can start making a quick estimate that x squared has limits. Make an estimate for yourself as I'm completing my statement here, but as x is getting to negative infinity, this function has limit positive infinity as well. Okay, and so again, let's quickly look at the graph. All right, so on the graph of this function right here, then as we're letting, and observe my mouse cursor again, as we're letting x getting further and further to the left-hand side, further to the left-hand side, or in other words, as we're letting x become more negatively larger, then the output value, and that's what the vertical height behavior of our graph is doing here. Our graph is keep rising up. But you see this time I'm going a little bit backward here. So as we're heading backward to the left side, our graph growing higher and growing higher and growing higher. And so that is graphically consistent. The answer that we observe graphically here is also consistent with our understanding that this limit has to be coming out to be positive infinity as well. Okay, and let's not rush. Let's look at another. And so we have only found the answer to 2 problems so far. And so this one right here is positive infinity. Okay, And then the earlier one, just a quick flashback, but the earlier one, x squared was a function, and we're finding limits of x squared as we're letting x getting to positive infinity, and that was also positive infinity. So I gave thorough explanations, but in the end we only found answers of 2 problems, and we haven't really formulated any general method to handle these problems yet. So be patient, and let's continue exploring some more. And then eventually, as you have seen enough, we're going to start putting it into some formulation of a technique. All right, so, and that's why any of these problems here, I'm just demonstrating the idea, but I have not considered any of these as a formal example. And so, what about, let's look at 1 over x. Okay, and let's consider the limit of 1 over x as we're letting x become, or letting x approach positive infinity. Positive infinity. And so let's now swing to my other board and construct a table of values. And after a table of values with some estimates at the end, we're going to quickly look at the graph again. All right, so the table value, left-hand side column is listing values for x. Right-hand side column is listing output values correspondingly. And so I can just famously start out with x equals 1, then the next one, x equals 10, then x equals 100, then x equals 1,000. Okay, and the value here, when we substitute 1 into the function, our function this time is a 1 over x. So 1 divided by 1 is 1. That's the output. But so now when x equals 10, 1 over 10 is 1/10. But normally I prefer fraction. But in some cases like this, let's bring this into a decimal so that we can have a sense about how these values turn out numerically. So 1/10 is actually a 0.1. It's a lot smaller, and as a matter of fact, about 10 times smaller than that already. And now when x equals 100, substitute it into the function, it's 1 over 100. But in actual decimal value, 0.01. And when it's x equals 1,000, substitute it into the function. We're looking at 1 over 1,000. And this is, in decimal, 0.001. And so now, once again, anyone watching this video should be having a clear estimate where this function is going. 1 over x has limits. Go ahead and make that estimate as I complete my statement here. So as we're letting x coming to or heading to positive infinity, then this function 1 over x has limits 0. All right, so computer takes time sometimes, so let's not use the computer screen, but right here, let me instantly bring up my hand sketch version of our famous 1 over x function. 1 over x function is this famous hyperbolic shape right here. And so on the x-axis, and this graph right here is the graph of 1 over x. So as x is getting further and further and further to the right end here, to the further end on the right, so getting further to keep getting to heading to positive infinity, then you see the function outputs getting lower, 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 and lower, and eventually it shrinks down vertically down to 0. And so once again, graphically, our result here is also agreeing with our answer that we estimated numerically. And so now we can make a final conclusion. This has limits 0 as we're letting x approach positive infinity. And then let's quickly look into another problem right here. 1 over x, the same function, but let's now find the limit as x getting to approaching negative infinity, meaning x value is heading to the left-hand side on the graph and keep getting further out to the left, further out to the left. Okay, And so I don't want to rush the answer here. Let's come over to the other board, and once again, let's work it out again. All right, so now table of values, our function remains 1 over x. Now I am going to choose x values that are showing heading to the negative infinity. So negative 1, we can start there, then negative 10, then negative 100, then negative 1,000. And that should be good enough. And in case we need more, we can just put in more values. But see, these values are all showing that they are getting, x value is getting further and further to negative infinity. The values of x is, the value of x is getting negatively larger. So when x equals negative 1, our answer is negative 1, because 1 divided by negative 1 is negative 1 for the output. Then here we're looking at negative 110 as the output, but negative 110 in decimal is a negative 0.1. Then we're looking at negative 1 over 100 when x equals negative 100 here. And the answer here is, and in decimal, I mean, is negative 0.01. And another one for here. This is output value negative 1 over 1,000. But in decimals, negative 0.001. So these are negative values. These are negative vertical values. It started out being negative 1, then negative 0.1, then negative 0.01, then negative 0.001. So now, estimation here, quickly estimating the answer, then we can see that in the long run, right, as we keep letting x heading further and further to negative infinity, then this function will go to limit 0 as well. It could be, it might look a little bit counterintuitive here, but you can see that these are negative, and the magnitude is getting smaller and smaller actually. So even though still being negative, but it's actually getting to 0. Okay? Excuse me. And so graphically again, the same function 1 over x. The right hand side piece is like this, but this time we're not looking at that right hand side. We want to particularly consider the left hand side of that 1 over x graph right here. So as we're letting x, so x is this time heading that way. Allow me to draw a kind of backward arrow over here, but the idea now is that as we keep negative infinity is that way. Okay? And so as x is getting further to negative infinity, see, negative infinity is out this way. And so our height started out being some negative height, but become still negative, but less negative, and less negative, and less negative. And now I'm talking strictly in terms of the vertical output value. And so that's how, looking through the graph here, the answer can also be agreeing, the answer is agreeing with this estimate that we've had earlier. All right, so now we're looking at this limit concluded to be a 0 as well. All right, so we've had about 4 problems. I'm not saying that we already found, if anyone found a way, good for you, but at this point, right at this moment in the video here, we still haven't found or haven't formulated any particular method to handle these limits problems. So these are just 4 particular problems on their own. We already found their answer, but we haven't recognized any general methods yet to find limits at infinity. But so now, allow me to start introducing a term right here. So strictly speaking, I mean mathematically speaking, we call these the limits at infinity. But graphically, if you're looking at the 4 problems all together, when we were doing the x squared right here, and so we were letting x approaching positive infinity, and then this is the behavior, and letting x approaching positive infinity means we want to find out how the function graphically behaves, how the function behaves as we keep navigating towards the right end. And I'm using that term as we're heading to the right end. We don't know how far it takes to get to the right end, but we want to investigate how the function behaves as we're heading out to the right end of that function. Same way, when we're letting x approaching, now allow me to, for the graphical purpose right here, then I have to use a backward arrow, but we want to let our x head out to negative infinity. So x approaching negative infinity means we're considering, we want to study how the function behaves when we're moving, when we're navigating our x values to the left end. And so for that reason, and same way with how we saw the earlier, the very recent example with the 1 over x function. So 1 over x function is this famous hyperbola, two pieces of hyperbolas, okay? But we did a problem where we're looking at x getting to positive infinity. See, x was heading out to the right end again. And same way, negative infinity is way back this way to the left, and we were letting x to head back to negative infinity. Now, yes, I do admit I'm using a little bit weird symbol, pretty out of ordinary right here, but I purposely want to graphically show that we want to head out to the left end, or here we want to head out to the right end. So in the end, limits at infinity, a lot of time being commonly referred to as, let me write it in red ink right here. Limits, any limits at infinity. So you gotta being referred to as and behavior. Okay. Of some function f of x. So that's generally how we refer to any limits at infinity problem. We refer to that as we're investigating, we're studying the and behaviors, and I should have used plural here, because we got two and behaviors. There's a left and behavior and there's a right and behavior. So particularly or generally speaking, any limits at infinity problem is being referred to as an and behaviors problem. We're looking at the and behaviors of the function f of x. And so specifically, more specifically, on any function f of x, and looking at the limits as x approaching positive infinity, this is now a lot of time being understood as this is the right and behavior. Okay, and similarly, if we're having a function, some function f of x, and we are looking at the limits of the function as we're letting x approach a negative infinity, this kind of problem is also understood as the left hand behavior, or that limit itself here is being understood as the left hand behavior of f of x. And both of these are of course, the function f of x. All right. And so now I bring up these terms for a reason, and allow me to take a moment to erase the board, and we'll be heading in that direction. All right, and so as soon as I start bringing up that terminologies that and behaviors, or in particular left and behavior or right and behavior, believe me, you have seen this concept before you enter calculus course here. You didn't have to wait until the calculus to understand what a left and behavior or what a right and behavior here. Maybe in your earlier course you weren't taught with the understanding of the limits concept. But now, let me bring back some old concept again, and it's algebra. So, anytime that you study the calculus with me, face to face or through an online, you will constantly hear me give you this advice here. You got to get your algebra going, because having 95% about there, 95% of your calculus learning is based on algebra, and the rest 5% is the remaining calculus stuff, the real calculus stuff. So you got to imagine how important you know your algebra before you can do well in your calculus courses here. But so let me remind you of this old concept I was saying right here. Let's say a function like this, or just simply the problem we did earlier, x squared, or maybe a little more generally, 5x cubed minus 4x squared plus 2. See, being the x squared function, or being some fancy one like 5x cubed minus 4x squared plus 2, or even maybe, I don't know, I'm running out of creativity right here. How about negative 1,000 x to the 10th, and then plus 3x to the 5th and minus 10. Okay? Any of these I brought up is a, remind yourself, any of these is a polynomials. So these are quick little examples of polynomials. So x squared is one member among the large family of polynomials. 5x cubed minus 4x squared plus 2 is also a polynomial. And allow me to entirely skip that notation, f of x and f of x. And then minus 1,000 x to the 10th plus 3x fifth minus 10. These are all polynomials. So what's in a polynomial? And I don't really mean to bring you all the way back to algebra, but the algebra teacher should have mentioned to you that a polynomial is a combination of all these powers of x, powers of x, powers of x. So it's just a combination of multiple terms, or it could even be just one single term. So let's not go way too far back into ultra basic stuff here, but let's even understand a little further. But polynomials, the highest power, see, in case it got multiple terms like these two bottom ones right here, we also, anytime looking at polynomials, we always tackle right into the highest power right here. And that defines what's so-called the degrees of your current polynomial. So this right here, since x squared is the only term, I have to say now what this is a polynomial of, this is degree 2, because the highest and the only power here involved here is the power 2. So this polynomial, one term polynomial, degree 2. This three terms polynomial, but we recognize that the highest power here involved is a power 3. And so this polynomial, the entire polynomial here, I'm now going to say this is a polynomial of degree 3. All right, so I hope that's a brief enough reminder for anyone about the degree of any polynomial. So guess what? This polynomial at the bottom of my list here is a degree 10. And I hope your own understanding agrees with mine right here. So that's how I briefly remind you about what the degree of any polynomial is. Now, the next thing I want to mention. So your algebra teacher also should have mentioned this, but anytime you're looking at a polynomial, you must, it's not really a strict must, but it's always the best idea to arrange all the terms here in either decreasing order, like how I'm more comfortable with, or increasing order. So here, see, if this is the only term, then that's the only way how it can be. But there's the 5x cubed minus 4x squared plus 2. See, I already wrote my polynomial in the decreasing power order right there. And so same here, I wrote my three terms here in the decreasing order of all the powers right here. So I start the highest power I've got here was power 10, and then there's power 5, and then so on and so on. So I wrote them. It's always the best practice to write your polynomial in either increasing or decreasing order of powers. Okay. So now the reason I mentioned about that now is once you put your polynomial in a certain order where it clearly shows where the highest power is, then in other terminologies, these numbers, these values right in front of each of yours, x term right there, well, x cubed, x squared, these are all coefficients. Minus 4 here is a coefficient. Plus 2 here is a constant, but it's also a coefficient. So now this particular coefficient here for the highest power, I refer to that as leading coefficient. Leading coefficient. Okay, so same way here in my bottom polynomial on the list here, the highest power is here, the power 10. So leading coefficient is 1,000. So this, I mean negative 1,000. So this negative 1,000 is my leading coefficient. All right, and allow me not to go too far back into tearing it down. So what exactly is leading coefficient word by word? So leading coefficient for this term, this one single term polynomial, you don't see the power. I mean, you don't see the coefficient, but it means really it means a positive 1. Agree? And so this is also that positive 1 is the leading coefficient. So that's one more reminder. So now allow me to erase all this. All right, and so what I'm about to introduce here, believe me again, it's not anything brand new. You didn't have to wait until calculus to see this. So you should have seen this way back in your college algebra course, but here it never hurt to remind us. So once in a while I can remind anyone about this. But so back in your days learning algebra, there was this famous table over here. Let's look at some summary. Some table that summary and behaviors, okay, and behaviors of polynomial. Okay, so and behaviors of polynomial. It's an old concept you have seen. So now, to determine the and behaviors of any polynomial, it's surprisingly simple. What matters, what determines the and behavior of any polynomial depends on two factors. Either it has an even degree, okay, or having an odd degree. I'm talking about your polynomial. Is it having an even degree or an odd degree? Okay, and besides even or odd degrees, we use another factor to determine the lead coefficient, whether the lead coefficient is being a positive number or being a negative number. That's all it matters. So whether a lead coefficient being positive or whether your lead coefficient is negative. So we will quickly walk through each of these cases here one by one, and we're going to investigate, and we will understand clearly the and behavior. So this quick chart that I'm constructing here, like I said, you should have seen that back in your algebra, but here we're going to go over this again and apply our limit understanding on top of that. So here I'm looking at the case where our polynomial, let's say, have an even degree like the power 2 or degree 4 or degree 10, and then what's happening when it has a lead coefficient being positive value. So now, allow me to turn on my graphing calculator here. Right, and so right now with our current one that still remains on my graphing calculator, the x squared function. This one here has what? Leading coefficient 1, positive leading coefficient, and even degree. But let's look at another one. So how about x to the 6, okay, minus 4x cubed, whichever degrees that comes after the actual degrees right here, whichever power that comes after the degree of the polynomial doesn't matter anymore. Okay, and let's say, maybe I zoomed it out a little too far. Okay, and so observe the graph as I'm typing out, and these functions I'm typing out right here are entirely out of my own creativity right here. It was not planned, but I want anyone to catch the idea that there's a truth that happens on any of these functions right here. But let's say I'm going to throw in a coefficient, how about positive 3? Okay, so no matter how I change, but as long as I stay with even degree and a positive leading coefficient, look at what happens with the graph right here. Right hand, as we've on this particular graph we have already seen, right hand as we navigating to the right hand. Okay, the right hand behavior of this graph, it grows up positively. So as we're navigating to the right end on this particular blue graph right here, the graph rises to positive infinity. And then as we're heading to the left end right here, the end behavior of this graph vertically, it's going to also rise. And of course, I'm not saying that these two are the same graphs. They're not the same graph, but x squared graph has the similar behavior, the similar end behaviors. Left end going up, right end also going up. Doesn't, regardless of whatever fancy thing going on in the middle. So see, the blue version here has some fancy up and down in the middle part, but in the end, the left end and right end, that's what we're learning right now. They're doing similar thing with the red curve right there. All right, so what's our little conclusion that we can draw here? Back to the chart that I'm constructing. So now when we're looking at even degree, any polynomial with even degree and combined with a positive leading coefficient, then the structure of the graph looks like this. Left end points up. See, I'm drawing my arrow, kind of slanted arrow, and you can see that when I was drawing it, I try to go to the right and head up. So right end points up. Whatever going on in the middle doesn't matter for us, not a matter for us, but left end also points up. Okay, so anything in the middle of these two end behaviors, that's not what we want to concern, but see, now we have a general understanding of the end behaviors on the kind of polynomial with even degree and positive combined with positive lead coefficient. And trust me, as I'm getting close, as I'm getting further onto this board right here, your memory will come back. All right, so what about when we have a combination between an even degree polynomial and a negative lead coefficient? Let's find out what's going to happen. I am going to switch back into my computer screen. All right, so this time let's put in some okay, we still want to be even degree, but negative. So how I can just quickly switch my current value here, my current function here, to a minus x squared, and here I can just change that to a how about negative 3, something like that. So now let me show the graph of the first one. All right, so this time we have a parabola that points down for the minus x squared function. And then let's quickly turn that off, and then turn the other graph on. All right, so the graph for minus 3x to the 6 minus 4x cubed plus x minus 2 is this blue one right here. Okay, and now we can put the two graphs together and let's see what they have in common. So as we're getting to the left end on both graphs, the left end points down as we're heading to the far left side, and far left side. And as we're heading to the right end, both of these graphs right here are vertically heading down as well. So now some general conclusion can be made here. All right, so now when our function still being an even function and combined with having a negative lead coefficient, then it looks like now of course we don't have to worry about what's going on in the middle body of the graph, but right end points down. Once again, observe the motion of how I drew my arrow. I was drawing to the right and headed down, and then left end behavior also point down. Okay, and so now generally speaking, anytime your polynomial is of an even degree combined with a negative lead coefficient, these two are describing this chart right here, describing the end behaviors of your polynomial with this combination of even degree and lead coefficient negative. All right, and so now what about, let's switch our attention over to those polynomials that have odd degree. So let's now look at, let me see how creative I can be here. So back on my screen, turn that off, and let's turn this off. Okay, so I'm going to create, say, a fifth power, okay, and positive coefficient, and here let's be a little wild here. Let's go with the power 9th, and but let's stick with positive lead coefficient. So positive 2, okay, plus and 5x to the about 6, okay, and really whatever fancy thing going on with these terms other than the lead term is not really important. That decides the graph. And so x to the 5th is this graph right here. Positive leading coefficient lead coefficient here is 1, but odd power this time, odd degree this time. And now let me quickly turn that off and turn the other one on. And of course, please don't get me wrong that I am not intending to make any one of you to know how to graph these things. Ooh, that will actually come much later in the quarter and we will learn that technique. But here we only need to quickly let the calculator handle the graphing for us. And so if you don't use decimals, your TI calculator, your standard calculator required in the class syllabus can help you draw the graph of these things just fine. But so now odd degree 9, with a positive leading coefficient being positive 2 right here. And look at the graph right here. Right end points up, left end points down. As I'm heading to the, see some funny zigzag waving up and down nature in the middle body. That's not what we want to concern about. But as we now eventually head ourselves to the left end right here, our graph is pointing down on the left, and our graph is heading up, pointing up on the right end point. And then let's see if it was the same back to our x to the 5th function. Yes, it was the same. So right end points up, left end points down. So now we are once again ready for a general conclusion here. So back into this chart here. And so for polynomials that are odd degree and combined with a lead coefficient being positive lead coefficient, then right end points up, and whatever going on in the middle body of the graph, not our concern, but left end points down. A lot of instructors, a lot of faculty, a lot of professors keep telling their students when your polynomial has odd degree, then the left and right end goes opposite direction. I have no objection. I'm not comfortable telling my student that, but yes, that's one way you can understand. And so that's how it is. And now let's quickly turn our focus to the other case and the very last case on this table. What happens when our degree is odd and combined with our lead coefficient being negative? Let's find out. And again, let's switch over to our screen here. Okay, so now I'm going to use, how about negative 3, okay, and here negative 2. Okay, so let's quickly turn on the graph here. So odd degree, negative lead coefficient. Look at what just happened to the graph. Right end this time points down and left end points up. So, and on the other hand right here, on the other function. So right end points down, left end points up, just like the red one I just now turned off. And once again, this one here has odd degree, negative leading coefficient. Okay, and so now let's quickly turn back to our table and ready for this last conclusion. So when your polynomial has odd degree combined with a negative lead coefficient, then right end points down and left end points up, as how you have seen that in the graphs just now. And that's why, like as I said earlier, many professors, and I have no objection with that at all, you're more than welcome to understand things that way. But anytime your polynomial has odd degree, then the two ends point in opposite directions. See? Either it's right end is up and left end is down, or right end is down and left end is up. So, well, since I mentioned it anyway, then it's also worth it to mention when it was even degree. Anytime it is even degree for any polynomial, then two ends have the same behavior. So the polynomial goes in the same direction for both ends. How's that? All right. So take a moment to take note on this, and we are now, and like I said, this is entirely algebra. I highly believe that anyone viewing this video have seen this chart way back at your pre-calculus course, your college algebra course, and we didn't have to wait until calculus to know this. Okay, and so now, how does that? Particularly, I meant the chart. How did that help us solving the limits at infinity problem? So let me now really bring anyone viewing this video into an actual example now. Example 1. So let's evaluate. Okay, so part A, and here in this one example, but I can create about 3 or 4 little problems. So x to the 5th power minus 4x squared, and really make sure you take note because this is completely out of my own creativity. So once I erase it, it's gone. So, and I just want to show anyone that how dynamic it is. You can quickly apply your understanding previously from algebra, now apply that into our calculus understanding. Okay, so coming out from my own creativity, we have a polynomial x to the 5th minus 4x squared plus 1. Let's evaluate this. Limits of this polynomial by letting x heading to positive infinity. It looks threatening at first, I admit, but here's the thing. This is how we can now at this point effectively apply our past algebraic understanding into this problem right here. This is a polynomial. I emphasize again, this is a polynomial. Odd degree, positive leading coefficient. Odd degree, positive leading coefficient. And I explained earlier before I put up that chart, before I reminded anyone about that chart, that limits, considering the limits problem as letting x approach positive infinity is nothing but just, or entirely can be understood as the right hand behavior problem. Right hand behavior problem. It was that exact concept you've seen way back in algebra, but we just never used that limit understanding, that's all. So polynomial, odd degree, positive leading coefficient, and we want to consider the right-hand behavior. We now have our chart to help us with that. Our chart now says with a polynomial having an odd degree, and when leading coefficient being positive, then the right end points up. So the right end points up. Now in our limit understanding, we're talking about this limit comes out to be a positive infinity. Ladies and gentlemen, that's how we can apply past algebraic understanding into doing a limits problem in calculus, entirely calculus work. All right, I'm going to leave the answer for that one there. Let's, in my remaining space, let's do another problem. How about let me challenge my own creativity. So x to the 4th, okay, but negative 3 plus 5x minus 3, okay? And let's evaluate the limits of this polynomial as we let x approach negative infinity. All right, so now at this point, set yourself into this correct pattern of understanding or correct behavior. Seeing this notation lim with the subscript x going to positive infinity or negative infinity, this is either a right-hand behavior problem or a left-hand behavior problem. And once we understanding your ultimate goal, let's look further into the kind of function you're having. What you're having here is a polynomial, even degree, with a negative lead coefficient. Now I'm ready to use that chart, that famous chart again. So with that famous chart being written here, then our polynomial is even degree, and it's having a negative lead coefficient. And we were looking at the left-hand behavior. So left-hand behavior on this kind of polynomial have to be a pointing down. Left hand points down. Left hand points down. So that means what? Back into our problem. The answer here must be negative infinity. That's how we can answer it. All right, and for these still in the same example, and whichever problem I'm bringing up here now, pause the video, have your own answer, and come back, resume the video, and compare with my answer here, and allow me to not switching back and forth between the boards anymore, because viewers will get tired of me doing that. So, part C, how about minus 3x to the 5th power plus 4x minus 50. Okay, and let's find limits as x is going to positive infinity. Okay, pause the video, have your own answer, and come back and compare with my answer. All right, you're back. My answer here is negative infinity. Okay, this is a right-hand behavior. Okay, my polynomial is odd degree with negative leading coefficient. All right, how about another problem? Question D. So all right, so something like this. Limit as x approaching negative infinity of the polynomial 5x to the 1000 minus 4x to the 90 minus 4x squared. Please, I don't even need anyone to graph this thing. Even if we have the super powerful computer, I don't want to look at the graph either. But the point now is that you should be able to find out the left-hand behavior of this polynomial based on the chart I just now reminded everyone. Go ahead, pause the answer. Pause the video, have your own answer, and we're going to come back with compare with my answer. All right, so hopefully you had your own answer. So my answer here for this is going to be positive infinity. And that's how just one algebraic, some fundamental algebraic understanding work. We've had a little while ago, before calculus. Back at that time, we thought, wasn't so useful, but this is now how it applies into calculus, and we already been able to answer quite a few and answer a lot of limits problem, limits at infinity problem, because that's what the concept, the end behaviors of a function.